Hey, Algebra 1. Today we are starting Chapter 6, and we are starting here with solving systems of equations by graphing. Okay, so we're going to go ahead and jump right into it. All right, so to start, we should probably define what a system of equations is. Okay, so a system of linear equations is going to be where we have two or more linear equations. And yeah, so two or more of them will form a system of linear equations, all right? And then any ordered pair that makes all the equations in a system true is a solution of a system of linear equations, all right? So like if we look at a graph and we have two lines like we see in problem 1, a solution to a system of linear equations would be where those lines or graphs intersect. Okay, so that would be this point right here at 2, 4 in this example on problem 1. All right. So yeah, that's the definition of a system of linear equations. And we'll just go ahead and get into how to use it. So we'll look here at problem 1, solving by graphing. All right. They give us y equals x plus 2 and y equals 3x minus 2. All right. So then they say just graph both equations in the same coordinate plane. They did that for you here. I'm not gonna go too much into it as far as me doing the graph and everything myself, because they've already got this one for you, and it's going to be a better quality than anything that I try to draw for you. As much as I have been revered for my artistic excellence, I think this is probably a better option for you. So, yeah, we've got y equals x plus 2. So there's the x plus 2. There's our y-intercept at positive 2. And then the slope is 1. Remember, there's an invisible 1 there. Okay, which is why our slope goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, all the way through. All right, then our other equation is y equals 3x minus 2. So we have our y-intercept here at minus 2. And then we have up 3 over 1, up 3 over 1. And that is our graph for both of those equations. All right, like it says, or like I said earlier, the next thing you want to do is find the point of intersection. Okay, these graphs intersect at the point 2, 4. All right, if you were going to check that, the way to check that would be to plug in to both of these equations. So like we have y equals x plus 2. We have y equals 3x minus 2. All right, we can just plug in our coordinates on both of them. So our y value is 4 equals our x value, which is 2, and then plus 2. And then we also have y equals 3 times x, which is 2, minus 2. Okay, now we just have to look and see if both of these are true. Okay, so 4 equals 2 plus 2 is 4, so that one's true, so we're good on that one. And then the other one, we have 4 equals 3 times 2 is 6, minus 2 is also 4. So that tells you that both of these are true, which means that this is a solution for this particular system. All right, that's really all you have to do on those. Go ahead and try out Got It Problem 1. All right, so you'll have to draw your graph and do what they did and what we did up here. All right, so do that and then we'll continue on. All right, so problem 2 is writing a system of equations. All right, so this is like a real world problem with biology. So scientists studied the weights of 2 alligators over a period of 12 months. The initial weight and growth of each alligator are shown below. After how many months did the alligators weigh the same amount? All right, so the first thing that we want to do is we want to write an equation for each of the 2 alligators. All right, so alligator 1, I'm going to put A1. We have that our initial weight is 4 pounds. Anytime you see something is initial, that just means that that is going to be your starting point, or what we're at when x is 0. And if you remember from our graphing, when x is 0, that is our y-intercept. All right, so if we have an equation in y equals mx plus b form, for alligator 1, our y-intercept is going to be 4. Okay. Our y stays the same, our x stays the same, so now all we need is our m. Our m is our rate of change, or our slope, which becomes really easy to see on this one because it's called rate of growth, which makes it pretty clear that that's our rate of change. Okay, so that would be 1.5. All right, and then if we look at alligator 2, and we use the same form of y equals mx plus b, all right, we're going to want to do the same sort of thing. So we have y stays the same and x stays the same. Our initial weight this time is 6 pounds. Okay, and then our rate of growth is 1 pound per month. So that would be 1x plus 6, or just y equals x plus 6. All right, so after we have our two equations for alligator 1 and alligator 2, we can graph both of the equations. And again, I'm just going to let you look at the graph that they have here for you, because it'll be easier to see. So if we graph that, you can see that the two equations, when they're graphed, they intersect at the point 410 right here. All right. So what that tells us is that after 4 months, both alligators are going to weigh 10 pounds. Okay, so our answer to their question that they had for us is going to be 4 months. Okay, go ahead and try out Got It problem 2. And then after you finish that, we will go ahead and move on again. All right, so the next part is that a system of equations that has at least one solution is consistent. Okay, and then a consistent system can either be independent or it can be dependent. All right, so just to give an idea of these a little bit further, consistent just means that they intersect at some point. All right, so an example of one that would be inconsistent, basically the only ones that will be inconsistent are the ones that are going to be parallel. All right, so if they're inconsistent, that means they're going to be parallel. All right. On the other hand, we have consistent, and then with inconsistent, we have either independent or dependent. All right. So an independent will have one solution. Okay. So this is an example of one, is they're just going to intersect just in one spot. All right. Whereas a dependent system of equations, all right, if it's linear, which is what we're dealing with, we're only dealing with the linear systems of equations. This means they're going to be the same line, so they'll have infinitely many solutions. Okay. All right. So yeah, that's basically the idea on that. And then if we go down to problem 3, we have systems with infinitely many or no solutions. All right. And then we can see, so if we look at A, we have 2y minus x equals 2 and y equals 1/2 x plus 1. All right. If you were to graph both of those on the coordinate plane, first of all, you're probably going to want to change this, change the form of it. All right. So in order to do that, I'm going to do 2y minus x equals 2. I'm going to add x to both sides, and I'm just going to try to isolate the variable y. All right. So then I have x plus 2, and I'm going to divide everything by 2 on both sides. So that'll leave me with y equals 1/2 x plus 1. And then our other equation, what do you know? They're the same equation, all right? So you would really just need to graph it once, and that'll tell you that there is infinitely many solutions because they are the exact same line. All right. And then if we look at example B here, let me erase this real quick. If we look at example B, we have y equals 2x plus 2 and y equals 2x minus 1. All right, well, if you think about our last few lessons, these two have the same slope. So what we learned about that is when we have the same slope, they're parallel. Okay? So we know that these are parallel, and because they have different y-intercepts, that means that they are not the same line, and they are parallel, so that means they will not intersect. Okay, and if they don't intersect, that means that it is inconsistent. All right, and that is really it for example B. Okay, and then here's a graph as well if you wanted to see a visual representation of it. All right, yeah, so that's it for that. Go ahead and try out Got It problem 3B, and then after that we are going to be done for this lesson. So it's a little bit shorter. Well, not as short as I thought it was. I felt like it was shorter, but that is it. So I will see you guys back in class, and yeah, that's it.